Okie doke. Okay. Towards smaller, faster decoder-only transformers, architectural variants, and their implications. In recent times, the research on large language models has grown exponentially, predominantly focusing on models underpinned by the transformer architecture, and further developed through the decoder-only models such as large language models. Contemporary efforts in this field primarily aim to enhance model capabilities by scaling up both architecture and data volumes utilized during training. However, there has been little exploration into reducing model sizes while maintaining their effectiveness. In this study, we introduced three modifications to the decoder-only transformer architecture, namely parallel GPT, linear GPT, and conv GPT. These variants demonstrate comparable performance to the conventional architecture, with LGPT outperforming in 4 out of 7 benchmarks with less than half the parameters. We open sourced the model weights and the complete codebase for these implementations for further research. An introduction. Since the debut of ChatGPT, there has been notable increase in research on large language models across a broad range of disciplines made possible by the accessibility of this technology to a diverse user base. This vastly growing field has largely pursued two distinct paths. One aims at either scaling the model size or the training data set, or both, to enhance performance, while the other concentrates on refining smaller models ranging from 1B to 7B parameters with high-quality data. Despite these advances, investigations into structural modifications of the transformer architecture itself have been relatively overlooked. Recent studies challenge the necessity of perpetually increasing model size by demonstrating that the deeper layers of LLMs may have minimal influence on predictive outcomes. In this work, we explore modifications to the decoder-only transformer architecture to address current challenges and scalability and practical application of large language models. Recognizing the significant impact of model size on the computational overhead of training and inference, we introduced the three variants: parallel GPT, linear GPT, and conv GPT, each designed to reduce parameter count while maintaining or potentially enhancing model performance. The models presented in this paper range from 30 million to 80 parameters. From 30M to 80 parameters? I'm guessing 30M to 80M parameters. Our decision to train models of these sizes was influenced by GPT-2, which marked the beginning of the GPT era. We aimed to introduce architectural variations within the vicinity of GPT-2's size to explore similar performance characteristics. Rather than striving for state-of-the-art results, our goal was to develop models with comparable parameters but reduced size, achieving performance similar to the traditional GPT architecture. We pre-trained each architectural variant on the 10 billion token subset of the FineWeb EDU dataset. The dataset was chosen to match the scale of the models we wanted to train. By training on a reasonably extensive dataset, we aimed to ensure that the models could be effectively evaluated on various benchmarks, thereby comparing the performance of different architectures. The remainder of this paper is organized as follows. The related works are discussed in Section 2. The modifications made to the base architecture and the reasons for the modifications are presented in Section 3. Experimental setup and the results are presented in Section 4. Section 5 discusses the limitations of the research, and finally Section 6 contains the conclusion of our work. Okay, so let's see, we have traditional GPT architecture, we've got the token embedding, positional encoding, summed together. We've got the decoder, and then classification head. The decoder is in instances. Related work. The evolution of large language models has been heavily influenced by advances in transformer architecture, first introduced by Vaswani et al., and later adopted into decoder-only models such as GPT. These models typically focus on scaling up using more complex architectures and larger datasets to improve performance. However, there's growing interest in designing models that maintain strong performance while being smaller and more efficient, addressing the need for models that are simpler to train and deploy. Our work introduced three new variants of the decoder-only transformer architecture aimed at improving training and inferencing efficiency: parallel GPT, linear GPT, and conv GPT. These models achieve similar performance to traditional transformer architectures text generation tasks, but with fewer parameters and faster training times. We have open sourced the model weights and codebase to support further research. Recent research also explores efficiency-focused architectures. For example, the funnel transformer reduces computational cost by compressing the sequence of hidden states through a pooling mechanism, allowing the model to expand in depth or width without increasing the overall cost. Compressing the sequence of hidden states through a pooling mechanism. The Mobilama model is another example optimized for use in resource-constrained settings. It uses a parameter sharing strategy within transformer blocks to minimize both pre-training and deployment costs, aligning with the goal of creating smaller, more efficient models. Innovative attention mechanisms have also contributed to more efficient LLMs. Grouped query attention reduces the complexity of attention calculations by grouping inputs, effectively lowering the computation from quadratic to linear, which helps in handling longer sequences. Multi-query attention further improves efficiency by allowing multiple queries within a single attention head, enhancing the model's ability to gather and process diverse information. These advances reflect a clear trend toward making LLMs not just more powerful, but also more adaptable to practical constraints like size and computational limits. Our work builds on this trend by exploring novel architecture modifications that offer a balance between performance and efficiency. 3. Architectural modifications. In this section, we introduce 3 novel architectures derived from the traditional GPT architecture to address various limitations in training and inference. These architectures are designed to enable faster training and inference. 3 proposed architectures are Parallel GPT, Linear GPT, and Comp GPT. Parallel GPT. In a traditional GPT architecture, the encoder blocks of the same dimensionality are stacked on top of each other. The drawback of such an architecture is that as n increases, the deeper blocks have little information to work with. Also, recent research point out that the inefficiency of the deeper layers, thereby questioning the need for increasing n. To overcome these drawbacks, we propose splitting the n-decoder blocks into p-parallel blocks, such that each parallel path p consists of n over p decoder blocks. Each p sub I has preceding dense layer, p times d sub I, to process the incoming token embeddings. The reason for introducing a dense layer before each parallel block is to make sure that each block learns something different. A vector of learnable weight, member of R, the reals, dimension p, is used to combine the outputs of each of the parallel blocks. The following set of equations give the mathematical representation of the architecture. Okay, h sub I equals p times d sub I of x for I1 to p. Y sub I equals f sub I of h sub I. So, okay, so h is the activation, yeah. What's the output from y? And activation exponential of the weights all over the sum of the exponential weights. Okay. So softmax. I believe that's softmax. We designed this architecture so that we can have the following benefits. Faster training, as each parallel block P sub I can be assigned to a separate compute node, allowing them to be trained in parallel. During inference, we have the flexibility to drop 0 to P minus 1 number of blocks based on the required inference speed, trading off some output quality for faster performance. A point to note here is that we have used a simple weighting mechanism for combining the outputs, but other methods like mixture of experts gating functions can also be used, which we leave for future research. Linear GPT. As discussed in 1, the earlier layers contribute more to the generation capabilities of an LLM than the deeper layers. This questions the need for each decoder block having the same dimension, as this results in the model having much more parameters than it is actually needed for the desired performance. The extra parameters of the model might also result in the model overfitting to the training set, which LLMs are known to do. To address these issues, we propose an architecture, LGPT, in which the dimension of the decoder blocks keeps reducing by half as the embedding of the token passes through the architecture. This concept is inspired from the continuous downsampling of images in CNNs for a task like image classification. To make sure that the dimension of the embedding of the token does not get too small by the time it reaches the classification head, we only reduce the dimension after every n number of decoder blocks. This is done by introducing a dense or linear layer after every n decoder blocks. The following equations 5, 6, and 7 give the mathematical representation for the architecture discussed. Here, d sub I represents the ith decoder block in n number of stacked decoder blocks, and equation 7 gives us the dimension d sub m of a vector before it goes through a decoder block. Okay, so h the pre-activation is equal to the decoder sub I of the previous activation for I 1 through n. hi is equal to the layer activation of previous or just the previous activation if I is equal to nj, otherwise it's just that previous activation. D sub m is equal to d naught over to the power m, where m is equal to the floor of capital N over little n. Parallel GPT. Got the token embedding, positional encoding, sum, and each one goes to multiple paths with weighted addition, and then a classification head. So an LGBT architecture can reduce the number of parameters in the model in terms of millions or billions. The reduction potential of this architecture is shown in Appendix A. In the experiments we did, the number of parameters in the traditional GPT architecture was 77.2 million parameters, while the LGBT architecture only had 36.4 million parameters. And it still performed competitively with GPT while outperforming it, COPA and ArcEasy, as shown in table 4. 3.3 ConvGPT. A one-dimensional convolution with kernel size and stride as 1 is a very similar operation when compared with the linear operation, as both of them have the same number of parameters to train, and both of them carry out a matrix multiplication of similar dimensions, but at a fundamental level both are different because of the positional context, spatial invariance, and weight sharing properties possessed by the convolutional operations. In order to find whether using one-dimensional convolution for compressing the dimensions has a performance difference compared to the traditional GPT and the previous architectures introduced, we introduce a third new architecture, cGPT, which replaces the linear compression layers in LGPT with a one-dimensional convolution layer. cGPT offers the same reduction in number of parameters as pGPT, and as can be seen from Table 4, it is competitive with the traditional GPT architecture. For our experimental setup and results, this section discusses the specific parameters we use for the experiments, the training parameters used, and the results of each architecture on various benchmarks. 4.1 Model Configuration. For each of the architecture, the common hyperparameters are set as illustrated in Table 1. For the pGPT architecture, we set the number of parallel blocks P in this experiment to 2, with each parallel path P sub I having 4 decoder blocks. For the LGBT and cGPT architectures, we set n number of blocks after which a linear or convolutional layer is introduced as 2, resulting in the final embedding dimension to be 32. The number of parameters and the memory requirements for each of the models are shown in Table 2, where pGPT1 refers to pGPT model in which the one parallel block is dropped. Note that during training, none of the parallel blocks are dropped. During inferencing and saving the model, 0 to p-1 blocks can be dropped to save time and memory. We have algorithmically illustrated the reduction potential of the pGPT architecture in Appendix B. Okay, so let's see, we got parameter context size, 1024, vocab size, in layer, in head, embedding dimensions, 512. Dropout, 0. Training. We train all the models in the same training setup which we have listed in Table 3. We use a cosine decay for the learning rate. We train each model for 5,000 steps, which is about 25% of the entire training set, and the training was stopped here as due to compute constraints. We train each model with on 4 times a 5,000 GPUs. With the GPT and pGPT architectures took about 2 hours to train, while LGBT and cGPT architectures took about 1 hour to train. 4.3 results. In this subsection, we present the loss curves and the evaluation results of our proposed model variants, comparing their performance on the following benchmarks. HelloSwag. Test the model's ability to understand common sense reasoning and continuation of textual descriptions, evaluating how well the model predicts the next plausible sentence in narrative-like sequences. Measures Winogrand measures the model's performance on pronoun resolution tasks, which challenges the model's understanding of context and disambiguation of pronouns in complex sentences. Common sense QA, fuck. Focus on evaluating models' general common sense knowledge and reasoning abilities, particularly in answering multiple choice questions based on everyday scenarios. ANLI, adversarial natural language inference, tests the model's robustness and understanding of natural language inference under adversarial conditions, requiring the model to distinguish between entailment, contradiction, and neutral statements. PICA. Physical interaction question answering evaluates the model's grasp of physical common sense reasoning, specifically how well it can predict plausible actions or outcomes related to everyday physical interactions. COPA, choice of plausible alternatives, assesses the model's ability to infer causality and select the more plausible of two alternatives outcomes given a premise testing causal reasoning skills. Test scientific ARC-easy, test scientific knowledge and reasoning in a simplified setting, focusing on how well the model can answer multiple choice questions related to elementary middle school science topics. Table 4 shows the performance of the various proposed architectures on a set of standard benchmarks. Note that the aim of this work is not to achieve state-of-the-art language models, since the scale of the models and data used in this work is very small compared to the state-of-the-art models. The goal of this research is to produce architectural variants that are smaller in size with similar model parameters and have a performance comparable to the traditional GPT architecture in the same training and evaluation environments. Comparison with traditional architecture. The results from the table indicate that the LGBT, CGPT, and PGPT-1 architectures perform competitively with the traditional GPT architecture. The PGPT-1 outperforms GPT on 5 out of the 7 benchmarks, while LGBT and CGPT outperforms GPT on 4 out of 7 benchmarks and 2 out of 7 benchmarks, respectively. Even on benchmarks that GPT outperforms the best, the other models perform competitively with GPT. We hypothesize that the possible reason for the competitive performance of the architectural variance is that the reduced number of parameters act as regularization and reduce the likelihood of the model overfitting to the training data, which is usually the case in the traditional decoder-only models, which can be prompted to output its training data. The results further indicate that even with reduced number of parameters, the architectural variants are competitive, thereby asking the following questions, which we believe future research will answer. Which components of the decoder are most critical for generative capabilities? Is it necessary to scale uniformly across all decoder blocks, or can varied dimensional scaling offer similar or improved results? Should we test different architecture designs before scaling the models? Figure 4. Comparison between PGPT and PGPT-1. From the results, it can be seen that PGPT-1 with just 4 decoder blocks is able to perform as well as the PGPT model with 8 decoder blocks. To further investigate if the network had learned to ignore the signal for one of the parallel paths and just use the signal path from the other parallel path, we check the final trained vector weight, W member of R squared. The weights of the parallel paths P1 and P2 were 0.5964 and 4036 respectively, which shows that the model used the signal from both paths during training, and the performance of the architecture remained robust during inference even when P2 was dropped. The results raise the following questions for future research. Does each parallel path model a different part of the knowledge, and if so, can an efficient mechanism be designed to process different sequences only with the required parallel paths? Can the PGPT architecture be leveraged to introduce domain knowledge more effectively compared to post-pre-training methods like LoRa? Specifically, can PGPT's unique parallel paths enable the direct integration of domain-specific knowledge during the pre-training stage by assigning dedicated blocks to learn varied domain aspects, or through the addition of specialized blocks post-pre-training, thus simplifying the process and enhancing model adaptability? 5. Conclusion. In this work, we presented 3 architectural variants of the traditional GPT architecture, aiming to investigate whether models with fewer parameters can achieve performance levels comparable to the original GPT. Our results across various benchmarks indicate that this is a promising and underexplored area of research. Through our findings, we raise critical questions and emphasize the need for further exploration. We believe that advancing this line of research is crucial, as AI can only reach its full potential to benefit humanity when it becomes widely accessible. A goal hindered by the high training and inference costs of large models today. Limitations. While our proposed architectures demonstrate promising results, several limitations should be noted. Lack of comparative analysis with SOTA models. The architectural variants have not been directly compared to state-of-the-art models due to resource constraints. While our research focuses on architectures of GPT-2 scale, direct comparisons with SOTA models could provide critical insights into the performance and efficiency of the proposed variants. Computational resource constraints. Due to computational scale limitations, the training of our models was stopped after what we determined to be a reasonable number of steps. Further experiments with extended training durations on larger compute setups are necessary to explore the limits of these architectures. Scalability and applicability. The scalability of the proposed architectures to larger model sizes and datasets remains untested. While effective at smaller scales, the performance and efficiency of PGPT, LGBT, and CGPT in large-scale real-world applications need further investigation. Future work should explore how these models adapt when scaled up or deployed in complex scenarios. Impact of simplified weighting mechanisms. The use of simple weighting for combining outputs from parallel paths in PGPT may not fully exploit the architecture's potential. Future research could explore more sophisticated methods such as gating mechanisms on or a mixture of experts to enhance the model's performance and adaptability. Despite these limitations, our work provides valuable insights into architectural innovations in transformer models and opens new avenues for research. Hmm. 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 Reduction potential LGBT. Section we illustrate the reduction potential possessed by the LGBT architecture. The Python below illustrates the algorithm we use for calculating the number of parameters in the traditional GPT architecture and the LGBT architecture. Calculate parameters and reduction config layer red equal to GPT parameters calculation embedding params equals config.vocab size.config.in embed block params config dot in layer times 12 times config.embed var 2 plus config.embed if config.bias else 0 classification head params equals config.in embed times config.vocab size GPT params equals embedding param. We count the parameters in both the GPT and LGBT models. All the parameters as following. The vocab size is 5,000 or 50,304. Context length is 1,024. Embedding dimension is 1,600. Number of layers is 48, and the number of heads is 16. In the LGBT architecture, we reduce the dimension after every 12 blocks so that the embedding dimension does not become too small. The following results demonstrate the effectiveness of LGBT in reducing the overall model size. Results show that LGBT architecture can reduce the number of parameters in the model by more than 1 billion parameters for the same configuration parameters. We leave the comparison of models of this scale for future research due to compute constraints. In this section, we illustrate the reduction potential possessed by the GPT architecture, PGPT architecture. Python code given below illustrates the algorithm we use for calculating the number of parameters in the traditional GPT architecture and the PGPT architecture. We count the parameters in both the GPT and PGPT model. The parameters as following. The vocab size is 50,304, context length is 1,024, embedding dimension is 1,600, number of layers is 48, and the number of heads is 16. In the PGPT architecture, we introduce 8 parallel paths and calculate the parameters during inference, assuming 4 parallel paths are dropped. Following results demonstrate the effectiveness of PGPT in reducing the overall model size. GPT parameters, it's over, 1.6 million. PGPT parameters, wow, less than 0.2 million. Reduction size almost near 90%. Results show that PGPT architecture can reduce the number of parameters in the model by almost 1.5 billion parameters, same configuration parameters. We leave the comparison models of this scale for future research due to compute constraints. Yeah. Well, yeah, I mean, it's not exactly what I was expecting, but good to keep in mind, I suppose. Good info. I do need to read the original transformer architecture again. Is this one what they're referring to? This one at all, yeah. All right, well, short session. Good night.